Thank you for the introduction. It's a great pleasure for me to speak in this very nice place, very nice center. I would like to thank the organizers for inviting me. I'll talk about quantum chaos. But quantum chaos can mean different things. One of the interpretation of quantum chaos is eigenvalue chaos, like random matrix theory. And this is not the topic of my talk, and I'll explain how it's different from my focus. Random eigenvalues mean that we have to resolve energies down to the many-body energy level spacing. And resolving energy to such accuracy means measuring something on a long time, very long, because when we consider many-body system, the energy level spacing scales exponentially. And this long-time behavior has very little to do with classical physics. I want to focus on a phenomena that occur at shorter times. If we compare to classical systems, it will be the Ehrenfest time. I'll explain what the Ehrenfest time means. But the main focus will be, of course, the SYK model, which is an example of a large N system, a system with a large number of simple degrees of freedom that interact with each other. And such systems also exhibit some kind of semi-classical behavior. So there is a parallel between quantum chaos and classical chaos for such systems. I would like to start with classical chaos and focus on simple models of classical chaos, because chaotic dynamics can be complex, but in some examples, it's well understood. Actually, there is a mathematical theory that was developed some 50 years ago, and I'll try to explain the basic ideas of its theory without much rigor. And in the last three lectures, I'll talk about the SYK model. This model is a simple model of quantum chaos in the same way as Arnold's cat map is a simple model of classical chaos. I'll talk about that later. So, what is chaos? If we consider a dynamical system given by some Hamiltonian, I'll write down some concrete Hamiltonians later, but just look pretty abstractly. Let's consider a pendulum. And it has a coordinate q and a momentum p. We can consider a two-dimensional pendulum with two coordinates, q1 and q2. And if we approximate it by a harmonic oscillator, then the trajectory will look like this. It's an ellipse. If we go beyond the harmonic approximation, or if we introduce a Hamiltonian like this, plus u of r, the radial coordinate, then the behavior will be slightly different. It's not an ellipse, but still a regular vector. And this is because the system is integrable. It has integrals of motion, the angular momentum, and of course the energy. And integrable systems have well understood behavior. If we fix the values of m and e, then there will be a torus in the phase space, and the system will evolve along the torus. It will wrap around the torus, generally along a incommensurate direction. But if we change this potential and we can break the rotational symmetry, then this behavior will be complex. And you've probably seen such demonstrations. This is an example of chaotic behavior, at least in some cases. There are three features of chaotic behavior. One feature is sensitivity to initial condition. And if there is noise or some uncertainty, the system will forget the initial condition. And the first property can be characterized by the Lyapunov exponent. Let me denote it by kappa. And the second property is characterized by Kolmogorov-Sinai entropy. The Lyapunov exponent means that if we take 2 points, say point x, and it will evolve in time, and it will be x of t. And let's consider epitope version of this evolution. And if we consider x tilde of t, that scales as e to the kappa t generically. For a chaotic system. And generically, it means that if the initial conditions are not specially chosen, then the scaling will be like this for short times. Or for a certain range of t. And for an illustration, let me write down some Hamiltonian. Let's consider H some coefficient A times P times Q. And the equations of motion will be Q dot equals AQ. And I'm using just the Hamilton equation. And, and, uh, and, uh, 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 and, 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 uh, the equations of motion will be So the system behaves like this. I'm starting with the basics, and hopefully at some point it will no longer be such a trivial thing. But this is generic, and that is special. So in this case, I mean x of t, q of t. Let me just use this notation. X in G. So it's a general Hamiltonian system, and x represents a point in the phase space. And in this case, we have one point that stays put, and another point, x tilde. And if the initial conditions are chosen such that Q naught is not zero, then the system will follow this trajectory, and the distance between x and x tilde will grow. But in a special case, it won't grow. It will decrease. And this is a very simple example, and it's not an example of the kind I want to study, because in this case, the phase space is infinite, and we would like to consider something with a finite phase space, such that the system doesn't go too far in Q or in P. And if we just fix Q and P and try to find the motion, then the system will enter a periodic trajectory, and there will be no chaos and no instability. So this behavior only occurs at this special point in the phase space. And to really construct a chaotic system with time-independent Hamiltonian, we need two coordinates, Q1 and Q2, and the two corresponding momentum. Let me introduce the general formalism. Of course, it's not anything new, it's just the Hamiltonian mechanics. I'll just write down some basic equations, and we'll use those equations. We have a point in the phase space, and we want to define a dynamical system formula. And it will be time evolution plus invariant measure. And the time evolution can be continuous or discrete, and continuous time each component of this vector has a certain time derivative, and d over dt x of j can be written like this. It's lambda jk d partial h over partial xk. And lambda has some plus ones and minus ones according to the structure of Hamiltonian mechanics. And we can write it like this. So this encodes two different types of Hamilton equations. One for coordinate moment, for generalized coordinate, and one for the generalized momentum. And invariant measure can be something like W of x e to the n x. So it's the phase volume element, and Wx is some probability distribution. And this probability distribution can be thermal, for example. So we can write Wx like but this is just one possibility. One can consider non-thermal distributions. But it's nice to have a probability measure such that the total measure is finite in particular one. If the phase volume is infinite and the system is allowed to access different parts of the phase volume, then things become more complex. So this is the setting which we can understand more or less. Everything simple so far. If you have questions? Yes.
Invariant measure is invariant with respect to what?
Invariant with respect to the time evolution. Okay, this is continuous time, and if we consider systems with continuous time, as I said, we need at least two coordinates and two momenta to produce an example of a chaotic system. And, such examples are more complex than examples with discrete time. With discrete time, we can produce nice examples with just two coordinates instead of four. So it's useful to consider discrete time evolution. And here I have to introduce some formalism, which is again standard, and probably know it, but I want to remind it. Even if we start with the continuous time evolution, we can integrate it over some period of time and obtain something like this. X of t is some function of x of 0. And let me put t on top. It's a function of two variables, of the time and the initial condition. If we fix t, say t is 1, and let's consider f1, and let's call it simply f. This f is a canonical transformation, or a symplectic map of coordinates and momentum. And symplectic map means that f preserves the symplectic form, which is and this can be written like this. It's 1/2, and I'll use implicit sum. Or indices like in this equation. And it will be lambda minus 1 jk dxj which dxk, and f preserves omega means that if we pull this form back using f, it can be written like df xj and this is and that is also a simple expression. Then this should be equal to f. And these two things being equal can be written as an identity for the derivative matrix.
Omega f.
Oh, omega, yeah, omega. So the equation is if we put lambda minus 1, interpret it as a matrix. And we're multiplying this matrix and that matrix. So this is the derivative. Yeah.
What is f star?
Oh, F star. I'm using some math notation, which is not important here, but it's the pullback of a differential form. So if you look at the matrix indices, this index K and that index K match each other nicely, such that this matrix is multiplied by that matrix in this order. And this is F prime, and this is F prime transpose. And it is multiplied on the left. So this is the condition that the symplectic form is preserved. And one can also say that F prime is a symplectic matrix. Now, what is a symplectic matrix? The answer depends on the number of dimensions. If we only have one pair of canonical coordinates, this condition is invariant. It is equivalent to the condition that the determinant of F prime equals 1. In general, it's an implication. A symplectic matrix has unit determinant, which means that it preserves the phase volume. And if there is only one pair of coordinates, it's equivalent, but for more coordinates, it's not equivalent. And it's useful to say something about eigenvalues of symplectic matrices. If we have a 2 by 2 matrix with unit determinant, then its eigenvalues are like lambda and lambda minus 1. Lambda can be a real number or a complex number, but there is a pair of eigenvalues. A general symplectic matrix has also pairs of eigenvalues, like lambda 1, lambda 1 minus 1, lambda 2 minus 1, and so on. The eigenvalues always come in pairs, like lambda and lambda to the minus 1. So now let's consider dynamical systems with discrete time.
Question.
Yeah.
From what is written about this symplectic matrix, it seems that what we need is just derivatives.
Yes. Yes.
So, I mean, f itself, not derivative, but f itself, what kind of meaning it has?
Oh, F is a map defined by this equation.
Okay.
It's some nonlinear map in general. But the discrete time evolution it says x of t plus 1 equals f of x of t. And we can integrate this equation and get that x of t, if f to the t of x of 0, the same equation, but now it's literally the map f applied t times, and t can be positive or negative. The system can evolve in both directions in time. Now, with discrete time, constructing invariant measures is not so straightforward. At least there is no unique choice of an invariant measure because the energy is not conserved, no physically natural choice. One can consider concrete examples, and in those examples there are natural invariant measures, but just by example. So let's start constructing such examples. Simple examples. And the first example is Arnold's cat map. It's a very famous example. Takes Q and P, a vector of Q and P, to this vector but as written, this map acts on the infinite plane, infinite phase space. It's not a nice example because a natural invariant measure, which is the uniform measure, will be infinite. And to make it finite, let's take the quotient. Let's say that Q plus K plus L is equivalent to what is this Q and P. So we're taking the quotient of the plane with respect to integer translations. And then we can write modulo the integer lattice. Z squared means the integer lattice in the Q and P coordinates. Now, when we take this quotient of the whole plane with respect to integer translations, we get a torus, two-dimensional torus. So F is a map of two-dimensional torus to itself, and this T2 is the plane divided by integer translations. And Arnold illustrated this map by drawing a picture of a cat, and then the cat gets deformed by the map. I'm not good at drawing, so I'll just draw a circle and show you how it is deformed. this square is the fundamental domain of this translational group. And it will represent the torus, meaning that this side is glued to that side, and the top is glued to the bottom. And we can introduce this fundamental domain in different ways. For example, it can be from 0 to 1, or from -1/2 to 1/2, it doesn't matter. And this is some set X, and it will be a circle instead of a cat. And this map is a linear map, and the corresponding matrix is symplectic, of course. The eigenvalues of this matrix are lambda plus is 3 plus square root of 5 over 2, and lambda minus is 3 minus square root of 5 over 2. And these are powers of the golden ratio. The eigenvalues are like tau squared, where tau is the golden ratio, and tau to the -2.
When you say the matrix is symplectic, you mean it's an exponential?
No, it is symplectic. In this case, it is unideterminate. And, in 2 dimensions, any unimodular matrix is symplectic.
It's already an exponential.
Okay, we just had this definition for F to be a symplectic map in terms of F prime to be a symplectic matrix.
Yeah,
Now,
this is F prime.
this is F prime. Okay.
So, this matrix has various eigenvalues. One eigenvalue is greater than 1, the other is less than 1. And there are corresponding eigenvectors. And this map stretches everything in one direction and squeezes things in the other direction. And if we stretch this circle and squeeze it in the perpendicular direction, we get an ellipse. It shouldn't be exactly diagonal, and this is important not to put it on the diagonal. So let me redraw this picture. This is f of x. And we can iterate, and we can plot f squared of x. We need to stretch more and squeeze it more, but when we stretch it, it becomes bigger than the fundamental domain, and the leftovers will show here. So this map starts wrapping around the torus. It also becomes thinner. This is f squared. And if we continue, then we'll get something like it will be very thin in one direction and very long in the other direction. And it will wrap around the torus. This corresponds to n of x. And we can continue iterate it in the opposite direction, and it becomes thing in the first direction and one in the other direction. So this is f minus 1. This is an example of a map which has non-trivial Lyapunov exponent, even though it's a two-dimensional dynamical system. As I say, when the time evolution is discrete, the conservation of energy is no longer relevant, and we can construct simpler results. The Lyapunov exponent is simply the logarithm of lambda. Lyapunov exponent kappa is logarithm of lambda plus. Because when we iterate, things get stretched in one direction, and it's like this. Of course, this is not a complete description of this map. This equation, I mean, there are more interesting properties to it. This equation suggests that the behavior of a point as it is iterated by this map is chaotic, and it is very unstable. However, if we consider a trajectory and fix the trajectory rather than the initial point with some flexibility, then the system becomes very stable. And this is something new. Let's consider this problem more carefully. We take points like x of 0, x of 1, x of minus 1, and consider points in both directions in time. And then we allow some flexibility. We say that x tilde can deviate from x by epsilon at any time, from some time t minus to some time t plus. So the problem will be formulated like this. X t is equal to f to the t of x of 0 and x tilde t goes from t minus to t plus, and let's assume that t minus is negative for 0, and t plus is greater or equal to 0. And let's impose this condition. X tilde of t minus x of t is less or equal to epsilon. And this will be fixed. Yeah, and this can vary. And let's try to locate all points satisfying those equations. The answer depends on epsilon. When epsilon is small, it's one answer. When epsilon is large, it's a different answer. And to solve this equation, I'll repeat the drawing, but let me erase it first because I want to do something very specific. In the end, it will look very similar. So we have a condition x tilde of 0 here, which means x tilde belongs to d epsilon plus x. This is a circle of radius epsilon. It can be a ball of radius epsilon in high dimensions. And this condition will be let me plot the set of solutions to the first condition. And the second will be in red. And in this case, we have to apply f to the minus 1, because the equation is about the point evolved forward in time, but we're asking it something about the initial point. So the equation is to characterize all points x tilde of 0, whereas the condition is imposed on x tilde of 1, and for this reason, we have to use f to the minus 1. And the set of joint solutions will be the intersection. And we can continue, and we can consider f minus 2 of u epsilon plus x2. And the intersection will be even thinner. And in the end, it will become a line within this green circle. But this pattern holds for small epsilon. And if we choose epsilon very big, the pattern will change. So this is the set of solutions to the first equation in terms of x tilde 0. And the set of solutions to the second equation, everything is in terms of x tilde 0. This will be something like and we have to wrap it around. The intersection is no longer connected. There will be different parts of the intersection. One part is in the middle. It looks like the previous picture, but there will be some extra solutions here and there on the sides. And the conclusion is if we impose all those conditions and epsilon is small enough, then nearby trajectories are highly constrained. But if epsilon is large, then they're not so well constrained because there will be some extra solutions like those. And one can formulate this conclusion if epsilon is small, then x tilde equals x tilde of 0 is given by x I'm sorry, I confused this symbol f minus 1, but I used f squared and f simply. So to change this, let me just put minus 1 here. Then the picture will become correct.
And then x of minus 2 was also.
And yeah, and instead of f to the minus 2, it should be f squared.
Yes, yes, but x of minus 2.
Oh, yeah, x of minus 2, yes. Thank you. And in this picture, we have two coordinates, x plus the ideal direction corresponding to lambda plus, and x minus is the contracting direction. And the solutions are described by these equations or inequalities. X tilde minus x the plus coordinate is bounded by lambda plus to the minus t plus, and for the forward evolution. And for the backward evolution, x minus minus x minus is bounded by lambda minus to the t minus, and this inequality corresponds to the pictures, because here we're constraining x minus, and x plus can still vary in a pretty broad range. Yes.
Can you remind me what is
Remind what?
B sub epsilon.
B sub epsilon is the unit ball of radius epsilon.
in which direction is the positive Lagrange exponent? This one or
The positive Lagrange exponent expands everything in this direction, and we're using f, f squared, and so on. But the indices are opposite on the x. It's x of minus 1, x of minus 2, and so on. Yes.
Maybe it's a stupid question, but does this come from our distance measure, which is not very well to us? Because we make a local measure for the distance of those states, which has not the same topology as our gate space.
I'm not sure.
So we are wrapping the space in white coordinates, but our epsilon does not go across this board.
I'm sorry, I don't understand the question. But since there is a question, maybe I'll repeat the formulation of your problem, and we can connect. So the problem is formulated like this. We're not thinking about a single point. We're thinking about a trajectory. And there is one given trajectory, x of t is fixed. And we allow x to that to vary, and x tilde can vary at a range of t's, from t minus to t plus. And we're fixing not a single point, but we're trying to fix many points at the same time. So it's not a problem about the single point. Yes.
Is x1 also fixed, or is it unfixed?
X1? Yeah. Everything without a tilde is fixed.
is this basically equivalent to just asking what is the set of initial conditions that will create trajectories in this given time interval that are all close to the corresponding trajectory that is fixed.
Yes.
And this way, what you're basically saying is that it suffices to know the range of initial conditions and then calculate the trajectory using the evolution equation. That's why you have these kind of conditions.
Yeah, but I'm solving the inverse problem. I'm trying to figure out what the initial conditions should be such that the systems... Yeah.
These two conditions that you have written there, they should both apply. So
Yes. Yeah, right. So the second condition responds to evolving the system back in time. And here I only used t equal to 0, -1, and -2. But in principle, we could also go to positive t's, 1, 2, 3, and so on. And then we have to use the first condition. Yes.
What is x plus and x minus?
X plus and x minus are the projections of x onto the unstable and stable directions respectively.
X is being multiplied by x, or is it hidden in the
X,
the bounds? Should they be multiplied by x, or?
right. It's by the order of magnitude. So indeed, we can write epsilon.
Maybe I can repeat my question.
Yeah, sure.
So our measure of the distance of 2 points is bound by square root 2. It's not, has a limit. So if I remove the boundary conditions, I can stretch this forever. I will never re-enter this sphere. So how should I formulate? So I have a curved space, but my epsilon my distance definition is a bit strange.
So you can define distance on the torus, but if you want to allow more flexibility, then we can just say that instead of E epsilon, we can have any shape. It's not necessarily a circle, it can be any shape. And then it doesn't matter whether the distance, if we go one way on the torus, is the shortest distance. The constraint on x tilde will be given by this epsilon, which is any shape we want. For example, instead of a circle whose radius is constrained such that we cannot make it too big, we can use this shape. And we can continue it, we can stretch it and squeeze it, and it will be a valid problem. Okay, so the conclusion is that the cat map is rather simple in the sense that if we consider a whole trajectory or a trajectory for some interval of times, and we impose constraints on all the members of the trajectory, then we're constraining the initial point very strongly. And this will help a subsequent calculation of Kolmogorov-Sinai entropy, which I mentioned. But to introduce this concept, let me consider an even simpler example. It's simple, but unfortunately it's unphysical because the map is discontinuous. It's called Baker's map because it has an analogy with kneading dough. A baker would press the dough and fold it. This is the picture of the map. So, now instead of a torus, we just have a square. And let's partition this square into parts of A0 and A1. And first, we change the coordinates like this. We squeeze the square in the vertical direction, stretch it in the horizontal direction. This is Q prime equals 2 times Q, and P prime equals Q. Now, we will continue and introduce, let me call this A0 prime and A1 prime, because this is not the whole story. To construct F, we need another step. Now we put A1 prime on top of A0 prime. And now it's A0, A1 double prime. Let me just say it's Q double prime and P double prime. This is a very simple map, and it can be characterized using binary code. If we use binary code for Q0, Q in the form.
Alexei, I'm sorry, how you want this last picture?
The last picture, I just cut it along the vertical line and put A1 prime on top of A0 prime.
Ah,
It's a discontinuous map. One can write a formula, but it will have two cases.
but how this action is related to the previous one when you go from P to P prime?
we just composed these two maps. It's just the composition of step 1 and step 2.
Ah, it's 2 step. Ah.
Yeah. So suppose that Q0 has this binary code. This is the binary point, and there will be some symbols after the binary point. A0, alpha 0, alpha 1, and so on. And it can be written as and P will have this binary code. Alpha minus 1, alpha minus 2, and so on. Let's write Q prime and P prime, and then we'll write Q double prime and P double prime. Q prime is we're multiplying Q by 2 and dividing P by 2, and this is the alpha 0. The integer part is just alpha 0, and the fractional part consists of alpha 1, alpha 2, and so on. This is the binary code. And here we're dividing by 2, so after the binary dot, it will be 0, alpha minus 1, alpha minus 2, and so on. And then to construct Q double prime and P double prime, we need to implement this step. Whether we are in the first part or in the second part depends on the integer part of Q prime. So the integer part is this, it's alpha 0. And we simply transfer alpha 0 to the binary code of P prime. If alpha 0 is 0, then it's 2Q, just say Q prime, P prime, if alpha 0 is 0, and it's Q prime minus 1, prime plus 1 if alpha 0 is 1. So Q double prime is the binary point alpha 1, alpha 2, and so on. And P double prime.
Maybe 5 prime plus 1/2.
Excuse me?
5 prime equals 5 prime plus 1/2 if alpha 0.
Yeah, it's plus 1/2, yeah.
No.
5 prime plus 1/2.
Oh, plus 1/2, yeah, thank you. So it's alpha 0 of the binary point, alpha 1, alpha 2,
Maybe alpha minus 1.
minus 1, minus 2, yeah. Thank you. So we see that the overall map transfers alpha 0 from the first binary code to the second binary code. And it would just formally write the binary code like this. X is represented by binary point alpha 0, alpha 1, alpha 2, dot, 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 alpha minus 1, alpha minus 2. Then f of x differs from that by the position of the binary point. This whole sequence is shifted to the left by 1 unit. And this kind of map defines a connection between a dynamical system and a stat-mech model. Because we can consider the uniform probability distribution in the phase space in terms of K and Q, and it's mapped to some probability distribution on those codes. And in the case of Baker's map, the probability on the codes will be uniform. Each digit is 0 with probability 1/2 and 1 with probability 1/2. So it's like a random sequence of zeros and ones, and the map is just a shift of that random sequence. In more complex examples, I'll explain what it means exactly. One can also construct a probability distribution of binary codes, or maybe not binary, but more complex codes, symbolic codes. And a dynamical system defines some stat-mech model on those symbols. In this case, this stat-mech model is very, very simple. There is no interaction with the probability distribution of those symbols. Like the Bernoulli distribution, all the symbols are independent. But this gives some insight into how the system forgets its past. Because suppose we look at the system and measure whether it is in the left part or in the right part. It means that we're measuring just a single digit, alpha 0. When the sequence is shifted, then alpha 0 is replaced by alpha 1, and the knowledge of alpha 0 doesn't help to predict alpha 1. We can try to do better. We can try to measure, say, 10 digits. But no matter how many digits we measure, some information will be lost because the sequence is shifted. And the symbol at the very left will necessarily be lost. And a new symbol occurs, which we don't know. We have not determined this symbol by our measurement. And the rate at which information disappears and new information comes into view does not depend on how many symbols we measure. We can take the limit of infinite number of symbols measured, which means infinite precision, but still information will be lost at the same rate. And this rate is log 1/2. It's the entropy per symbol. And that is exactly the Kolmogorov-Sinai entropy. I'm not giving a formal distribution, but the Kolmogorov-Sinai entropy. And in this case, it's log 2. Each application of the Baker map results in this amount of information loss. So there is this concept of information loss that is related to the Lyapunov exponent. The information is lost because, on the one hand, everything is Trajan squeezed. On the other hand, our precision is bounded, and we necessarily introduce errors that will be amplified in the future. But when we go to quantum mechanics, there will be an exact analog of the Lyapunov exponent, but I'm not aware of an exact analog of the Kolmogorov-Sinai entropy. It seems that the situation is not completely symmetric. So that is why I'm going through those definitions. Maybe you will find some nice quantum interpretation of the Kolmogorov-Sinai for many Borel counts. But let me return to the harmonic scale. In this case, or in other cases, one can introduce a partition of this system.
Sorry.
You can make it significant. So let's consider some phase space. And let's partition it somehow. The parts will be called A0 and A sub r minus 1. And then we'll consider symbolic code. Of x, and it's defined like this. Alpha of x equals alpha 0 of x, alpha 1 of x, alpha minus 1 of x, and it's continued in both directions. And alpha sub t of x is defined like this. It's equal to a if and only if f to the t of x belongs to a sub little a. This is a direct generalization of this picture. Now, each symbol defines FQ of x with some accuracy. Because if we use finer and finer partitions, we'll be constraining FQ of x more strongly. And if the partition is fine enough, if the parts are smaller than a certain epsilon, then at least for the cat map, we know that the trajectory is stable if we fix each point. In this case, instead of saying that the point deviates from a reference trajectory by less than epsilon, we're saying that we know which part each point is in. We know that alpha say x tilde belongs to a sub alpha 0, f of x tilde belongs to a sub alpha 1, and f minus 1 of x tilde belongs to a sub alpha minus 1. We have the system of equation, we can locate x tilde pretty accurately. Again, this is under the assumption that the partition is finite. And in this case, we can calculate the rate at which the entropy is appropriate. And we can define the Kolmogorov semi-entropy in the following way. Now let me erase everything related to the vector map. Do it in general terms. X is mapped to alpha of x, and we can define the probability distribution on alpha sub t minus through alpha sub t plus. And let's call this probability distribution W. That depends, of course, on this parameters, t minus, t plus. And we can define the entropy of this probability distribution as this is the usual definition of the entropy. And we can consider this limit.
How do we understand some of the alpha here? Alpha is alpha of x.
This is alpha. And in the denominator, there will be the number of symbols. And this limit is exactly the Kolmogorov-Sinai entropy. And we can calculate it for the cat map. Yes.
But this probability distribution, which depends on alpha, does it know about the map we are looking at, or it's independent?
Yes, of course.
That's why I
Because this code alpha depends on the map through this definition.
No, sorry. We define this probability distribution in terms of alpha, in terms of some partition.
Yeah.
Spacing this partition itself depends on f that we assign.
No, the partition is a fixed partition.
Yeah, but it's only for alpha zero.
Yeah.
For others, it will be transformed by f.
Yeah, the sequence of actions is this. We have a map and an invariant measure. We choose a partition. The partition must be chosen sufficiently fine, smaller than epsilon. And then we do this calculation, and the result does not depend on the partition.
Probability distribution is defined on the partition.
The probability distribution depends on alpha, and implicitly it also depends on the partition. But the partition is not a random array. Alpha is the random array. Because there is a map that maps X to its symbolic code. Yeah.
Trying to understand what's this probability distribution, in what space this probability distribution.
In the space of sequences of zeros and ones,
Or not in that original space which we broke into, which was partitioned into pieces.
we have some probability distribution, the measure on the phase space.
That's not the same measure.
It is related. We pick a point randomly according to our measure on the phase space. And that point will have a symbolic code. The definition of the symbolic code it uses this partition, but the partition only has to be small enough. Little depends on the partition in the end. For a given partition, each point is mapped to a sequence of zeros and ones, or a sequence of codes that take on those values from 0 to r minus 1, those digits. And if the point is random, then the sequence of symbols is random. But it's random according to some probability distribution. And in general, say for the cat map, there will be some correlations between those symbols because it may not be possible to have x in one part and f of x in some given part, and that will forbid certain symbols to be adjacent to each other. But on longer distances between symbols, there will be some randomness. So the definition is that we pick x at random and map it to, basically we evolve this x.
I understand how this map works. I do not understand what this function double from the sum is. What's the value of this function?
The value of yeah, it's the measure of A. Let me put those symbols of T minus through alpha T plus. And this measure can be defined as, this set can be defined as the intersection of a T going from T minus to T plus A sub alpha t. This is our original measure.
Should we have some restriction on R, for example, R grows with T plus and T minus or not?
Alpha
So we can choose trivial partition, yes.
Yeah.
So all set is just after 0.
Yeah.
So, but for example, for breaking map, we can choose partition with halves. Yes. So we see that in some sense the centropy at the beginning depends on the partition. What should happen with physical intuition behind that the centropy doesn't depend on the partition.
It does not depend on the partition, only if the partition is fine enough. If the parts are smaller than a certain epsilon.
Should this epsilon depend on the T?
Epsilon does not depend on T. Epsilon depends on the map. And the point is, if we trace a point backward and forward in time, and consider those intersections. Those intersections are exactly like in this picture. Those sets should be small enough such that the intersections are simple. If the intersection consists of disjoint parts, then the trajectory is not constrained by symbolic code. So that was a connection to the cat net. The cat net requires that the parts are smaller than a certain size to make the trajectory constrained. Yeah, and now I can show you the final answer for this homomorphism treatment for the cat net. This set, alpha t minus 1, alpha t minus alpha t plus, is exactly given by those intersections. And we know the constraints like x plus it's minus t plus x minus and the measure will scale as lambda plus to minus t plus minus t minus minus 1. And this measure is exactly the probability in this formula. And if we just plug it into the formula, then all we care about is this number, which is approximately equal to log lambda plus minus t plus minus t minus plus 1. And if we divide, take the limit, and we get that the homomorphism entropy is equal to log lambda plus.
Sorry, how did it happen that it's lambda plus
lambda minus is just lambda plus to the minus 1. Yeah.
Yes, and I have a question about the limit on delta x minus. So if lambda minus is smaller than unity and t is negative, that means that our constraint on delta x minus is infinite. So there should be probably minus t minus.
T minus is negative.
And lambda 1 is 1 over lambda plus, it's smaller than 1.
Oh, it's minus here.
Yeah.
Yeah, thank you. T minus. No, sorry. Lambda minus is less than 1.
Yes.
T minus is negative. It should be minus.
Minus h.
And yeah, and we should multiply these two numbers.
And revert
Excuse me?
no question.
Okay, so in the end we get this formula for the entropy. So we have in this simple model we have a connection between the Lyapunov exponent and the Kolmogorov entropy. And there is a class of systems described by this kind of theory. They are called Anosov systems, or hyperbolic systems. And we'll try to construct something analogous in the quantum world. Sorry for running out of time. Yeah.